I'm going to go over some of the online equilibrium homework answers. Hopefully this will clear up any misunderstandings you might still have. If you look at question number 1, this is simply a matter of plugging in your equilibrium concentrations. They've already given you the molarity. Remember, brackets mean molarity, and when you're using your values to plug in for your K, you must have either molarity or pressure for Kp. So this is just plugging in your NO2 concentration, being sure to square it, dividing it by N2O4, and getting a K value of 8.57 times 10 to the negative 3. Pretty small K value, indicating that when you've reached equilibrium, you still have mostly reactants. The second problem is putting in your values, okay, that you have initially, and then they give you an equilibrium value. So the first thing you have to do is make sure that you have converted those moles of A and B into molarity. So you've got 2 moles of A, 3 moles of B, divide by the 6-liter container, gives you 0.333 moles per liter of A and 0.500 moles per liter of B. Of course, you have no C. So when you look down at the equilibrium amount that they gave you for A, which was 0.246 moles per liter, you can see that A decreased by 0.087 moles per liter. That means you lost that amount of A. Looking at the mole ratio between A and B, you lost double that amount of B, or 0.174 moles per liter. And if you were solving for C, you would have gained the same number of moles per liter of C that you lost of A. You know that you lost A and B because of the equilibrium amount of A being smaller than the initial amount. So when you look for the equilibrium amount of B, take the initial 0.500, subtract the 0.174, and that gives you the equilibrium molarity of B. In question 3, you've got solid carbon, which is not going to be in the equilibrium expression, so you've simply got a ratio of 2 gases, CO2 and CO. And you've got a Kp for this reaction because instead of molarity, they're giving you the units in pressure. But the expression is still the same. Pressure of CO2 squared divided by pressure of CO squared divided by the pressure of CO2. Same equilibrium expression. You cannot use brackets. You need to use parentheses and write that P to show that you're talking about Kp and pressure. If you're not sure what you're solving for, write the equilibrium expression and then plug in everything that you have. You have the Kp value. You have the pressure of carbon dioxide. You're simply solving for the pressure of carbon monoxide. So it's an algebra problem that says the pressure of CO is the square root of Kp times the pressure of CO2. Gives you the pressure of CO at 5.34 atmospheres. Question number 4 is asking you to find the reaction quotient, or Q. Again, the math of this is done the same as the math of K. The only difference is that these are probably your initial amounts and definitely not your equilibrium amounts. So you find Q in order to decide which way your reaction is going to shift to reach equilibrium. So if you write your equilibrium expression, and again it's molarity, H squared times H2 times F2 divided by HF squared, and put in your molarities for those, then you get a Q value of 0.272. You then would compare your Q and your K to decide which direction your reaction would shift to reach equilibrium. The next equation has an equilibrium between 2 gases, three gases, NO2, NO, and O2. So write your equation out. At this point, they've given you again a Kp. All of your values are in pressure. So notice I've used parentheses instead of brackets. Write the expression. put the values in. You quickly see that this is, again, just an algebra problem. You have all the variables except one missing, the pressure of O2. By the time you plug and do your algebra, you get a pressure of O2 at 1.81. So you always benefit by writing that expression and seeing if this is a simple algebra problem or if it's going to require more work on your part. Question 6 is going to require a little more work on your part. Again, you have been given an equilibrium concentration. You have an equation. You have no K value. Okay? So they give you your initial concentrations, or excuse me, they only give you your initial moles per liter. You have to get your molarities. They give you the equilibrium concentration of A. So this is very similar to a previous problem. So you can see that in going from 0.333 molar to 0.213 moles per liter, you've lost 0.12 moles per liter. You lost double that of B, and of course for C, you gained exactly the same mole ratio of A that you lost. So when you're given an equilibrium amount, the problem is nothing more than seeing how your initial and your equilibrium compare to decide if your change is losing reactant and gaining product. You then write your equilibrium expression, put the values in. Don't forget to square the value for B because of the coefficient, and you get a K value of 8.33. Question number 7. This one's a little tricky because they've given you molarities, but they've also given you volumes of these. So this problem probably gave you some difficulty since you haven't had much experience. You would first have to get the moles of A and B, and then the new molarity from the total volume, and that would be your initial. So if you look for A, you see that you've got 45 milliliters of 0.05 molar. Multiplying your molarity times your volume in liters gives you 0.00225 moles. For B, you've got 25 milliliters of 0.1 molar, so that gives you 0.0025 moles. And then you need to divide both of these by the total volume, which would be 70 milliliters or 0.07 liters, and that gives you your molarity of A and B. They gave you the concentration of C already in molarity. So you had no C or D initially. So you calculate your A and B molarities. You look down and put your C molarity that they give you at 0.0410. So if you went from 0 to 0.0410, you must have gained 0.0410 moles per liter of C. You gained twice that of D because of the, not twice that of D. You've got a 3 to 2 mole ratio. So you can see up in the corner to the right there, I showed the ratio to get your 0.0273 moles per liter of D. Then on the left, you lost, okay, species B in the same ratio that you gained species D. So that's 0.0273. And then you lost species A at 1/3 the ratio of C. So this problem has a lot of converting to molarities and then comparing all the different mole ratios. So there's some tedious work there. It's all based on that equilibrium amount they gave you and the mole ratios between all those species and C. And then, of course, in the beginning, making sure that you had converted A and B into molarities. Once you get all of those to their equilibrium amounts by losing and gaining, then you plug into your equilibrium expression. So then you have to remember to cube and square your values. Eventually, you come up with a K value of 0.0397. So there are a lot of places you could go wrong in a problem like this. This is just building your skill with these types of problems. In question number 8, they've given you moles again, but this time they were nice enough to give it to you in a 1-liter container. So notice they gave you moles for nitrogen and hydrogen, but for ammonia, they gave you molarity. So you want to make sure, especially if the volume of that container is not the same, that you take the time to make sure that you're always in molarity for everything. So for hydrogen and nitrogen, you had 4 molar, 2 molar solutions. You have no ammonia to start with. You end up with 0.55 moles per liter of ammonia that's given in the problem. So you can quickly see that you gained that much on the product side, which means that you lose on the reactant side. And you lose in the same mole ratio that you always have for stoichiometry. Up in the right-hand corner, I've showed you that for nitrogen, you've got half the molarity. And then, of course, for hydrogen, you've got a 3-to-2 mole ratio. So making sure that you lose on the reactant side and gain on the product side, you get your equilibrium amounts, write your expression, put your values in, making sure to cube and square, and you get a K of 5.48 times 10 to the negative 3. Again, indicating that when this reaction has reached equilibrium at this temperature, you still have mostly reactants. And you can see in the problem the equilibrium values you do have. You went from 4 molar down to only 3.175, 2 molar to 1.725, and you only gained 0.55 ammonia. In question 9, this one is again pretty straightforward. You've got to get your moles divided by your 3 liters, so you get your molarity. They gave you an equilibrium amount of C, so that means you had to gain 0.115 moles per liter C, and your mole ratios for B and A. So if you gain C, then you gain B and lose A. So your equilibrium concentration of A would be your 1 molar minus your 0.345 moles per liter, leaving you with 0.655 moles per liter. So these kind of problems, those are a lot of the variety you can have. There are other things, but it's simply getting used to what information do I have, what am I looking for, and what's the best way to get my answer. We'll work on plenty of these, and you will become as skilled as you need to be.